Hi everyone, and welcome to this new MLIR meeting. Today, River is going to present about a new front-end pattern language on top of the PDL bytecode.
Hello, I'm River. I'm at Google. Going to talk about PDLL, which is a pattern language. Oh, good. If I can. Okay, there we go. So PDLL. Let's run this one. It's a front-end DSL for writing MLIR pattern rewrites. And the interesting thing about it, or I guess the obvious thing from the name, is that instead of C++, the entire point is the codegen to PDL, which is an IR infrastructure for pattern rewrites written in MLIR. So there's no C++ generated, but it still allows for C++ or some other native code injection. And some nice caveat from that is that because PDL itself, the single L, because it's like a bytecode representation, you can actually provide these patterns and compile them and stuff at runtime. So the language itself, as we'll see in a little bit, is effectively designed as a high-level representation for MLIR constructs and pattern rewriter constructs. So this kind of comes out in the design of its language. The language itself, it takes a lot of things from MLIR formats, but also in the things that it's intended to represent, which is effectively everything that we have in MLIR. So it's like optional, variadic region successors, type conversions, all of that stuff is within bounds with what we want to do. But kind of aside from that is that don't really just want to build another language. One of the main goals is to have a good experience. So this is kind of like, we want to make sure that whatever we provide has the tools that people expect from a language. So like code completion, go to definition, formatting, all of the stuff that people are accustomed to. So I guess, the easy question is like, why are we doing this? So I mean, if you think about it kind of pragmatically, a lot of the complex rewrites in MLIR kind of require C++ or some kind of like the C++ API because they're necessarily complex. But there are a class of use cases that can benefit from things being done declaratively. You could think of like instruction selection in LLVM, or if you think about ML programs, a lot of those really benefit from kind of a declarative specification for rewrites. So we kind of recognize that these users exist, and we want to provide something that is a good experience for them. So, I mean, recently, well, recent is a relative term, obviously, but when we were implementing PDL and providing PDL, we started to think about like, what is going to target PDL upstream, really, because it's intended for multiple front ends, but like, what are we going to provide as like the default thing that's always available? So that kind of spawned into PDLL. So I mean, the first thing to think about, or I guess question is, why not just use the tablegen DRR, which is what is currently available. But if anyone has ever used tablegen, you probably have mixed feelings about it, especially because tablegen's not really good for MLIR. Kind of sucks, really. Well, sucks is relative, but a lot of like problems have come out of tablegen with even like simplistic things like multi-result operations, which are like basic MLIR things. Not even going into how you would represent like blocks or regions or anything remotely complex like that. So if you take even like a contrived example of like, I have this like 3-result operation and I just want to like match some of the results, you have to like bind them all to one name and then use like this magic like __ number to be, that actually __2 actually means that it's like the second result group of this result, which is kind of hacky-ish, or at least I don't feel good about it. looking at it. But if you were going to do this in like a more sane programming language, and this is kind of spoilers for kind of a little bit of what PDLL looks like, you could have variables and then access results of those variables, because operations are conceptually like structs or tuples or things like that in other languages. And because obviously this is something a bit more modern, you get code completion and documentation and all of that stuff pulled directly from ODS. So all of that stuff's available. So it's not as annoying or confusing to write, at least ideally. So if we're not going to use TableGen, what are we going to do? There's obviously a lot of different options out there. And a lot of times people ask, why not X? And X here is kind of factored into the no and the yes and no at the bottom, which is that X means something different depending on who you ask, because different people think of different things. So X could be like Python, it could be Rust, it could be Haskell if you're in that crowd. And when you're kind of picking a host language for DSL, there's a lot of things that you have to kind of keep in mind, especially when you're going to distribute this in an ecosystem like LLVM, like we are intending to. So different host languages kind of have different dependencies. They can have different environments, performance, that we might not want to constrain on all of users or all of the places that we want to deploy the language, for example. But not just that, tooling is also a very important one, because one of the intentions behind this is to provide a good development experience, good being relative or subjective. And if you're building tooling into a custom DSL that's embedded in a host language, if your DSL doesn't really map directly to the host language's concepts, then your tooling is going to suffer like hugely. And especially if you're in an established environment, such as like a company or corporation or even a team that has like language servers or other development tools built around those languages already, they don't usually take kindly to, hey, let me inject my custom tooling for this simple DSL into like the main Python language handling. Usually they say no to that stuff. So we kind of made the decision that to kind of provide the best experience and to be able to deploy in all the places that we want to, then having something custom is not that bad, and it's kind of it's easier to kind of achieve the goals we have in mind for it. But obviously, the flip side is that PDL itself was designed around multiple front ends existing. So that's kind of a recognition that different users have different constraints, not necessarily the ones that we're placing on ourselves, but just want to make sure that we're still open to having multiple front ends, and PDLL is kind of intended to serve as kind of like a baseline in terms of pushing PDL forward, and also in terms of kind of establishing a baseline of features that you should provide if you're doing a front end. So it's kind of on the fence about what to show for the language itself, whether to have like 80 slides or to just have code and have people's eyes glaze over. So I chose the eyes glazing over one because that one's technically easier for me. So I'm gonna bore you with code of what it looks like, because I feel like that's at least more interesting to look at than slides, and it has better formatting and syntax highlighting and all of that stuff. So this part of the presentation is kind of freeform, mainly because I don't have any sleep, but it could go fast, it could go slow. People can interrupt and ask questions, or if they want to see something. So I don't really care about being interrupted, that's fine. So I'll just kind of go through this huge file of examples and kind of just talk about some of the different aspects to give an idea of kind of what the language looks like, and at least what we have in mind initially for it. So starting from like a baseline include files. So one of the key things here is that we want to be able to import stuff from ODS easily, because we want to avoid duplication of things, obviously, because it's a different language. But we don't want to have to duplicate anything that users have already expressed. So here I have including like a few Tableton files. And from there, we kind of import like what operations you have defined, what dialects you have defined, interfaces, traits, constraints, all of that stuff, attributes, types, all of that, so that it's immediately usable. And that kind of helps the experience. It's not technically required, but it's extremely useful. So from there, I can kind of go into like patterns, which are obviously the most important part of the language if it's intended for pattern rewriting. And just like C++, patterns have, like technically like 3 main components. They have like an optional name for like debugging, or depending on how you're generating, it can be useful to have a name. They can have metadata, which is things like benefits or recursion. So if you're writing a pattern, you might have like benefit attached or bounded recursion. So these are basically what you would see in C++ if you're writing C++ pattern, the types of metadata that you can attach. And then you have the body. And the body of a pattern is conceptually similar to C++. You have a match section and then like a rewrite section. And the match section is important because it's describing your input IR. So you can see here, don't pay attention to what these patterns are doing. Most of them are just things to illustrate concepts. But if we're kind of describing like potentially a reshape of a reshape, then you might have like an input operation that's your reshape, and it might take as an input a reshape that takes this this argument, which is the input value. So that is conceptually your match. And then a rewrite, you might want to replace this root operation here with like a reshape of the argument that you have bound. So the rewrite section traditionally is like the last statement of your pattern that kind of starts the rewrite. So in like a replace, the roots is just like an expression for an operation, and that is still technically like your match. But after that, anything with that you're replacing it with is going to be created. So if you have like an operation expression in the match section, obviously that's an input operation. But if you're like in the rewrite section, you're creating IR. So it's the difference between like checking if an operation is like a specific type versus creating one. But then, you can write that in a much simpler form if you want. And even simple patterns can be like inlined into one line. So that's like a quick example of patterns. It's not terribly complex, hopefully, just the things inside of it. So then metadata, like I showed before, benefit and recursion are the major ones that MLIR has right now, but if more get added, more can be supported, that kind of thing. So maybe obvious from the examples before, but there are variables. And variables in PDLL are strongly typed. And the types here correspond to IR constructs. So things like values, operation types, all of that stuff. And the types come from these constraints. And there's a few kind of like built-in constraints that give you the IR construct, and these things are the ones that imply the type. So these are the gold version ones here. Are some examples of them. So attributes, operations, types, values, etc. And then from there, you can kind of compose to make more complex constraints. And I'll go over that a bit later, but those can be things that are imported externally. So if you define them in C++ and register them, but you can also define them in PDLL itself and other things like that.
River, how do the native callbacks work? Is that something that you register like you kind of at runtime pass a C++ function pointer into the PDL infra?
Yeah, let me go down here. So, right, constraints, like I said, can either be defined in PDLL, which is just more of describing the input or like constraint, and these constraints don't really turn into anything. They all get inline. They're like functions, that kind of thing. But if you have like an external constraint, like I was showing before, these are things that are registered with the C++ API by the user. So this is something that the user has to like explicitly say, here's a mapping. It's like a JIT.
Yeah, it's like you pass in the string external constraint and a function pointer, basically.
Effectively, yeah. So, these ones are the ones that the user is like providing as part of the library, and you're kind of just importing that fact. Or you can kind of like DRR define them directly. So if you're doing kind of like an AOT code generation where you how like TableGen does today, where you're like, okay, I'm generating something that's included in the CPP file. If you're doing that, in PDLL, you can like inline the C++ blob if you want, and we'll auto-generate that and develop the wrappers for like, oh, you don't want like a generic interpreter value, you want like an actual attribute or a value, kind of like here, for example. So it kind of just makes it simpler in the simple cases to just like, I just want to call a C++ function. I don't have to deal with like registering with the interpreter and stuff like that. But we still want to leave that open in case, if we're calling from like a different language, or if you already had like a library of things that you register, things like that.
Nice.
And that also applies with rewrites, but I can go over that later. Right. So what I was showing with the constraints, the ones that you define, anything that takes like a single argument. So these are the core constraints, as they call them, which is like value range, those types of things. Or, if you've defined a constraint and it takes a single input, those can be used to like directly on the variable definition itself. So here, you have value in one use. But if we were going to do something like, like cast op interface takes an operation conceptually because it checks if it's an interface. Or you could use has one use directly because we know, hey, value is an actual value because that's the type of the argument. So this helps in the simple case if you're just like, I want to constrain this variable directly, and I know this has one argument, then that makes it easy in those cases. And I kind of showed it before, but you can define variables out of line, but you can also use an inline syntax. So if you ever use C#, it makes it very useful if you're kind of creating like DAG-like things where you don't want to have like inlines where it's just like, okay, I just want to have a value here. And this is especially useful if you're kind of like constraining operands for an operation, for example.
So River, perhaps just one question. So like in the previous one, like line 83, could you perhaps just sort of actually talk to it? What is that pattern doing?
I mean, the pattern itself, it's not particularly useful, but this one is kind of just matching this myDialect operation that has an argument and then replacing this operation with its value. So it's the same as this one, which is just, I've matched an operation that has an input, and I'm going to replace that operation with its input effectively. So, right, in this example, we've defined this variable inline. So we have this argument that's already constrained, and we want to check that the first and third arguments are the same thing. But the second value, and I'll go over why in a second, we don't care about. We just want to know it's there. So if you're kind of defining the operands of an operation, I'll go over this in a bit, but there's kind of two ways of doing it. The first is to have like a value range, which is like, okay, this is all the operands. But the second is to match what you've defined in ODS for the operand description. So this kind of maps directly to how you've defined the operation, because PDL is generic, so it needs to be able to map between these different constructs. So if you go to the operation itself, that's how it's been defined. So I've gone over it quite a bit, or at least shown a lot of examples of it. But if we consider like an operation expression, which is either in an input, it's like, is this operation and defining in the input IR like your root operation? And in the rewrite, it's modeling, what you want to create. So the syntax of this is expression, if it isn't obvious directly, is the exact same as the generic assembly format, like down to the letter. And that's kind of intentional so that when you're writing it, it's not confusing what constructs go where. If you've ever written generic IR, you at least have some idea of what constructs go where. So, this isn't all of it, but, I have operands, attributes, and the result types there. So you can have, you can have a named operation, which is, dialect.blah, or you can have it in your match. I want to match any operation, so I'm just not going to provide the type of it. And the reason why I had something here before is, if you're creating an operation expression, the nice thing is because this is like a real language, you can get code completion for all of the dialects that you have and all of the operations in those dialects and all of that stuff. So if you wanted to match like an arithmetic.constant, you could see that, go to its definition, all of that stuff. So hopefully makes it easier to write things as you're kind of going along because you don't have to guess what goes where. So I showed it before. So operands, you have two ways of writing them. One with a single value range or one which matches the ODS description. And if you have your ODS thing imported through like an include file, you obviously get like signature completion for what you're supposed to be putting there. So you don't have to guess what goes where, and you get the nice like autocomplete or code completion or signature help, whatever it's called, for what all of the different argument types mean. And results are conceptually the same thing, which is if you have the ODS description, you can get all the signature help, but there's two ways of doing it. One with the single type range, which is all of my results, or one that matches the description. And I showed it in kind of the introduction slides, but you can access these results by name. So if you're going to do .result, but you can also do it by index if you were in like a template or something and want it to be a bit more generic about what you're actually accessing. Okay. And then obviously one of the other things from the example that I showed is the attributes themselves, which again is exactly the same as the assembly format. So if you're going to add the attributes here, you can get autocomplete for the attributes that are expected and what the ODS description has for them. And unit attributes are the same thing. If you don't provide like an assigned value, it's just, well, I expect this to be a unit. Okay, so those are operation expressions, hopefully not too confusing in the constructs that they represent. Given that the syntax for it is exactly the same as the generic format, should be somewhat obvious, or at least similar to what you've seen before. But kind of going on from there, there's things to represent like literal MLIR attributes and types, because we're going to be generating PDL, which is MLIR. So it's trivial to just say, I want to create this attribute in MLIR because we're already generating IR anyways. So it's really trivial to kind of just inject these constant literals for different constructs that you want to have. I won't go over tuples too much, but it's basically a tuple if you've ever seen it in another language, which is like kind of an ordered collection of blobs or objects. And you can name the elements of the tuple directly, or you can just kind of leave them as is and kind of get the the generic, I would just index it by number. This is kind of like a common, like a glob of the way that different languages have tuples, just make it easier. Right. So I kind of showed this earlier when Sean had the question about constraints, but there's a few core ones for like attributes. If you want to constrain the type of an attribute, all of those things, operations. So you can have like a generic, any operation, or one that's constrained to, a specific dialect operation, type range, value range. So all of these represent kind of like core IR constructs themselves and imply like the type of a variable, because types in this language are directly correspondent to what you would have in the IR.
River, what is the erase up here? Is it the same as erase roots?
So this is why I say don't pay attention to it, because this is just this is just filler to make sure things compile and the system. This is basically, if you were to really write this, this is destroy everything, which could be interesting. But this is so this erase statement is basically erase all or erase this operation, which for this pattern would erase everything because the root has no name or anything constrained on it. So it's kind of like rm star.star, I guess, in a way.
But that's interesting though. Like that means that what would the pattern match here? What would be the roots because there needs to be a match before the erase.
So the erase, this part of the erase is considered part of the match because you're erasing something that's being matched.
Right. Okay. So that means that the match for the whole pattern would be everything, basically. That's what you mean. Right?
Conceptually, yeah.
And because we match everything, that we erase everything.
Yes.
Makes sense.
So then we can kind of show what I was showing Sean earlier, which is defining constraints in PDLL, and these are basically functions. If you've used any other kind of language, which is, if you want to have like a fragment of your match and share it across multiple different instances, or have something imported externally, things like that. I mean, they're like utility functions in a way, or like shared functionality. And then the native constraints.
Sorry, quick question. Can you come back to the last constraint stuff you showed? Yeah. What's the type of this multi-result thing? Is it a tuple or is it something else?
This one?
On the right-hand side of the arrow.
Right.
Value range. Yeah,
that's a good question. Yeah, it's effectively a tuple. So if we had, a result here, and we could call this directly, the result is effectively a tuple. Exactly as you were saying. That's kind of why tuples exist in the language anyways, is to kind of support this multi-result. So when you're defining the syntax, you're basically describing the structure of a tuple. So you're giving it a name here, kind of like a Swift does with multi-results, but you don't have to give it a name. And in this case, the return type of this inline constraint is inferred. So if you were going to have, inline constraint instead, it takes whatever type was returned. So if you have like a tuple here, then it's going to use that tuple. So if we did that, now we have like the name from it. So yeah, in the case of multiple results, it's effectively just a tuple that's being created.
I see. And the inference here happens because the definition in ODS of multi-result has two things, one result and one other result, which is value range in table gen or something.
So this inference right here, so the inference for the name comes from ODS. But for tuples themselves, tuples are outside of ODS because you're not, like for here, you could return like some like type adder or something. and you have like type adder here, and then let me call that. It's just the root. So you can access field 2. So tuples can be constructed with any variables, any values that you want, because it's just a collection of kind of IR values. The kind of named results, so doing like opt.results, those are the things that come from ODS to be able to do that, if that makes sense.
Okay, cool, awesome, thank you.
Right. So kind of going into the rewrites. So there's kind of 3 main ones right now. So like erase, replace, and rewrite. Erase is kind of what Manny asked about earlier, which is, if you have a pattern like this, erase, my dialect.foo, that will erase all instances of that operation. And if you have a replace, you're replacing some operation with some set of values. So in this case, these are values constrained to the first and third inputs that are being reused down here, because these are inline variable definitions. If we go to the definitions here, you can see where it's defined at right there. Yeah. And then rewrite is kind of conceptually similar. It's basically a way to have a block of some number of rewrite related things. So all this root does is kind of anchor the pattern at a specific operation, but inside of it is how you're actually going to transform the IR. So in here is all treated as like a rewrite. So you could have replacements, you could create other operations in here, anything like that. So this is just a giant rewrite scope, effectively. Right. And like constraints, rewrites can be defined as well, and rewrites are called from the rewrite section. So if you had a simple rewrite that was going to create like my dialect.foo operation, then you could call that with a specific value. And this is obviously a very simple example, but the rewrites could be as arbitrarily complex as you want and do effectively anything you want, create anything, call into C++, whatever. And the native rewrites are exactly.
Can you make line 392 fail to compile, I guess, or something? If you return there, create foo op, return an extra after, and you try to replace in it, what do we see?
So if you were going to do something like, like that, right? It's expecting a kind of an operation expression or something else.
Okay, so it's going to complain right there that there's an utter, it doesn't know about it, doesn't expect it. Okay, awesome.
Yeah. So I think that's something that's interesting to show, because if you had like a value here that you constrained it to like an operation, and you're like, oh, actually it's an attribute, and it's going to be like, actually, no, that's not something that exists in this world. So yeah, I kind of glossed over it, maybe because I thought it was implied, but the nice thing about having like a real language is that you get error handling immediately instead of like a miscompile or like random C++ errors that just happen to pop up. So kind of one of the ideas is that anything that can be handled in terms of error handling is handled immediately. That is exactly the way that you expect. So this comes out in kind of everything. So if you were trying to use like an attribute for like a value, then it's like, okay, an attribute is not a value or value range. That doesn't work for this. Because if we think about kind of like the way that table GenDR works, because it's structured around like the arguments of your op, and arguments are either operands or attributes, people actually often get confused on where the attributes go and where the operands go, which has created miscompiles and other weird behavior. But the nice thing about modeling it after like the generic format is that A, it's obvious, and B, or obvious if you've used the generic form, and B, you get immediate error handling because something isn't happening the way it's supposed to. So I guess just benefits of not using something that's maybe not intended for that. So I kind of went fast through rewrites because conceptually they're the same structurally as constraints, so not horribly different in terms of how you define them or use them. I mean, rewrites obviously you can't use on a variable because it's not constraining the variable, it's transforming something.
Yeah, I have a question. It's a kind of a tangent. I don't know if we're ready to switch topics.
Oh, sure, Sean, you can.
Yeah, I'm curious, is the type interop, like, you know, custom types, attributes, like right now it's like, so that stuff is like really C++y, but like, is there any hope of, you know, being able to like, say you have like a, you know, HLO dot dimension numbers or like convolution parameters or something that has, you know, like a bunch of fields, being able to like check those easily in here and do like a little bit of math on them and stuff?
So you mean, I guess it depends, because like checking if something is like that attribute that exists, that's fine.
Mm-hmm.
Because it's kind of conceptually the same as like checking if something is like a specific, like if you're gonna do, I guess here's an example. So like all of the attributes, types, etc. that are defined in ODS are imported automatically. So in terms of like, is this like an HLO dimensions adder, or is it like a cat-top interface, or is it like something else? All of that stuff is fine. What kind of comes from there is we're kind of constrained by what we can reasonably generically support with PDL itself.
Yeah.
So in terms of falling back to kind of custom code, all of that's easy and supportable. But in terms of like doing the actual math in PDLL itself, then it kind of gets into like what built-ins we want to provide and what like of those types of things are.
I think there's also one other thing, which is the destructuring of the, like looking inside of the attributes. Like say you have like a struct adder that has like a bunch of fields. I guess we could improve the same for types, you know, the type and attribute ODS thing to sort of emit an interface that allows us to sort of reflect on some of those things at runtime, so then it becomes possible to like, you know, check if some struct at, you know, field foo of some struct adder is, you know, I32.
Yeah, exactly. I feel like a lot of things are going to come out of that, which is PDL itself, the underlying infra wants things generically because it has to support everything, and it's you know, anything that we want to do with it has to be through an interface or some other kind of generically accessible means. So if we want to start doing that kind of stuff, yeah, it's going to push like interface design, or at least generic accessibility of attributes, which can be beneficial in general concept.
Yeah. Yeah, totally. I think the Python bindings would also benefit.
Yeah. Kind of quickly go over templates. Templates are very similar to templates in other languages, except for the thing that can be a template type is something that's not an IR construct, but is something that's like statically known. So these are things like constraints, operation names, or rewrites. Those can all be passed in and kind of used directly. Here it's like passing in a different operation type for the root that's going to be replaced. In this case, it's a foo, and this is a bar. In this case, we pass in the name itself as the template type, and then pass that into an operation expression. And in the last case, very similar to the constraint, we've passed in kind of like a rewrite that is going to be called here. So slightly rather simplistic in here. It's passing in this specific rewrite as the template argument. So that's kind of how the template types and like constraint arguments, I guess, are kind of differentiated as whether it's like an IR object or whether it's something like static. Right, I think I have other examples of templates and things like that. Okay. So as a kind of a final example is some like range expression type things. So these are conceptually similar to like a range library or like a lot of the LLM utilities that might be used to constrain ranges. So these are things like, checking if all of the values of a value range satisfy some constraint, or if all of the values and types within a value or type range satisfy some constraints. Same with things like any of, checking if any elements satisfy some constraints, checking if ranges are empty. These are just a lot of like simplistic range things that are very useful if you're kind of building more complex patterns. None of, which is very similar. I think probably the more interesting ones are like the map functions, which can perform like reductions over values. So if you want to map all values to a constraint, it's actually conceptually similar to like all of in a way. Or they're almost identical in structure. But maps can also be applied to rewrites. If you want to kind of take a value, you could apply multiple different rewrites to it, so like create operations that use the value or the type or things like that. And then, as I kind of mentioned earlier, you can perform like reductions over it, which is you kind of map a value range over this. And so if this rewrite returns a value, in this case, this copy is actually a value range, which is a concatenated version of all of the elements. So whatever you created here just gets combined into like a giant list of things. And the same works for like if you were to return like a type range or something like that, they would all get concatenated into one giant type range. And then kind of a similar sister expression to map is this map if, which applies a constraint or rewrite if a constraint holds. So maybe you want to constrain like values that have one use differently than something else. So it kind of gives you like a subset or like some like structured control flow application to these things. So if you wanted to like apply some rewrites, so like create operations for like all of the shaped types of a type range, that's something that might be used for. Or like map could be used for like creating a tuple extract for all values of a value range or something like that. So these are kind of just like semi-control flow range expressions that are added, but it's kind of like getting into the more complex types of rewrites and things we want to support. And that's kind
so.
Yeah.
What can you map over? What's the type of the first? What types for the first for the container are supported? So value range, type range.
Any range is supported.
Integers.
So, like that's where it gets into what I was saying with Sean, which is it depends on what is a built-in construct in PDL and like what is supported. So right now PDL is all like IR constructs. So the types of ranges here are like value range, type range, and operation range for like users, things like that. Because there's no notion of like an integer or a float in PDL itself. So like these types of things depend on what we want to make as built-in. If we were going to like map over a range of integers, we would have to decide what that means.
Right, because it seems that since you already give us templates, you give us these ranges. If you give us just basic, next arithmetic, like I don't know, like axioms of natural numbers, right? We need a 0 and a +1. Then we can suddenly write all these nice unrolled things. Hey, if I have an 8x8 vector, unroll that to 64 versions of this thing.
Right.
For instance. Like that would be super useful. I would be happy to move all the vector rewrites into PDL.
Yeah, so this is, I can switch over to the slide itself. And that kind of goes into like the status of it. So I think this will partially answer why those things don't exist, which is that the current status right now is everything in the demo works and is supported. And kind of the initial feature set that's been focused on is, for example, like what would it take to kill TableGen DRR for like an example of the kind of features we're focusing on first. But then after that is like getting into the kind of crazier, more interesting things. So like if we had like kind of like a structured, like, okay, I want to iterate over, you know, I just want to apply some map function like 10 times to like unroll something, for example. And other things like blocks and regions or dialect conversion, type conversions, things like that, that all of these things are things that we want to support, but stuff that we kind of want to hopefully build on as we get like base things working. And this also applies to like making sure that PDL itself is optimal, or at least not slow, because PDL compiles at runtime. So it's kind of important. And that kind of goes into this, which is to give an introduction to the language kind of before we kind of formalize an RFC and develop upstream, because we don't want to have like a huge like drop of code. And also want to make sure the community can like factor in things like Nicholas, as you were saying, like, okay, I want to be able to, you know, iterate over like a range of numbers and apply some like rewrite or map function. Because these are the types of things that we want to have conversations for and hopefully have the design like done upstream and code review done upstream. And this is kind of why we've been focusing on initial feature sets, so can get like a base thing agreed upon, or at least ideally, and then kind of move from there. And that's all of the slides that I have.
Do you see this being used for name mangling as well?
Name mangling?
Yeah, for example, if you have multiple operations with the same name and you want to name mangle them so that there's no conflicts, for example, given an input source that can have multiple names at the same name. Like you could have a symbol table from another language which supports similar symbol names.
Right. I think ideally anything that doesn't require like super complex C++ is in bounds to support. So as long as it's reasonable, I don't think there's a no there. I think the things that we want to avoid is having the bytecode become like basically a CPU JIT in a way, if that makes sense. So as long as that doesn't happen, anything else is kind of in realm to support.
That would actually be kind of cool.
Dang it, Sean. Okay, as long as it's not like a full x86 JIT. I think some simple things are fine, but making sure we don't go the full route of absolute craziness.
Okay.
Yeah, like
So
one
if
thing
I-
I would like to do, like I'm literally writing this now, is I have a like a torch script module, and basically, you know, sometimes I might want to like interpret that, and so if there was like a sufficiently powerful interpreter, I know this keeps coming up, then, you know, I could compile that, at least like a compact bytecode, and have that. I know that's kind of a reach.
So if I understood correctly, the PDL is currently compiled to MLIR at runtime, and then the pattern matching is also executed at runtime using an interpreter, right?
Yep.
Are there any plans to also support some kind of ahead of time compilation, similar to how TableGen sort of functions today?
So the point behind PDL is that the PDL itself is compiled at runtime. Because I guess it depends. Like, we could support modes where it's pre-compiled, but there are different caveats there. One of them is that often it's useful to have the dialects that you're matching linked in to perform optimizations, like removing redundant computations or things like that. And another is the cases where you have a bunch of patterns being combined together. So, I mean, that's a lot of the benefit that you kind of gain from, or at least some of the benefit that you gain from like a bytecode abstraction that's compiled at runtime is, especially for MLIR, is that, you know, in canonicalization, you have patterns coming from like in different unknown sources. So if you compiled ahead of time, you might only have like one pattern, and that's not really going to give you a good benefit. You're not going to have any kind of redundancy elimination or any kind of useful merging. But if you had like one pass that has all of its patterns defined there, then yeah, in that case, compiling ahead of time is probably more useful. I think this kind of goes into the evolution of how we want PDL to look. It's semi-orthogonal to PDL itself, because it's a use case that I find interesting, but it's not something we've like scoped out in terms of like how to support it or how it would be supported. So I think it's plausible. It just hasn't been scoped out well in terms of PDL itself.
I have a question though, Marcus. Why would you want to AOT compile it?
It just seems like a much easier language to work with than the table-gen declarative rewrite at the moment. And if you were, and for a typical ahead of time compiler, you could then just, it would be a simple replacement for a table-gen driven one, which currently compiles to C++. And if you could use the PDL definition language to also compile to C++, I would expect similar performance from that.
So there's kind of like different things. So there's like compiling the PDL itself ahead of time, and then there's compiling it in a way that replaces table-gen ahead of time. So it supports modes where you like generate the C++ just like you would with table-gen to like add the patterns to your list and things like that. So all of that stuff is supported. So you could conceptually use it as an immediate drop-in for table-gen. Like it has the same like user-facing API in terms of like what you would add. So all of that is like supported. What's different is in if you compile the PDL bytecode itself ahead of time versus not, because it's slightly different.
So Marcus, your concern is mostly with performance. Like you're afraid that the bytecode interpretation is going to be slower than the code table-gen generates?
Sort of, yeah. I mean, if the bytecode would be fast enough, I don't want to assume that the bytecode or any runtime interpretation is going to be slow enough. I was just curious whether that's something
I mean,
that might be supported to do that.
It's worth watching the presentation on PDL itself about this, but a lot of the things that were underlying the development of PDL was the idea that by jitting the bytecode, first by compiling multiple patterns together in the bytecode, you can do CSC across matching, meaning like when you generate table-gen, there's a lot of redundancy, and we're going to match one pattern on the same op. There can be multiple patterns, and we're going to try to rematch over and over the same code. With PDL, because you have the global view, you can create a tree of matching and reduce the amount of redundancy. That's one thing. Another thing is that by jitting, you can start doing smart things. For example, you have already the context available. So if your matcher says, is this attribute, the unit attribute present, or is this a true? Like, for example, loop unroll, if my attribute is loop unroll true, because you already have the context when you JIT, you can get the pointer to the true attributes and replace this with a pointer comparison in the end, instead of, is this a Boolean, and then get the value, is it true, So there are a bunch of things that you can do in the JIT that would make it even potentially faster, much faster than this.
So instead of all the complicated conversion and pattern matching thing that is currently done in C++ that ensures that the patterns are transitively work, you could JIT compile all patterns in a sum and have faster patterns, so to say, as an end result due to the JITting?
Yeah, I'll send you a link to the previous presentation on the bytecode, because all those optimizations were presented last year, actually. Today is mostly the front-end part on top of it.
I see, okay.
It scales better. If you have one C++ pattern, it's probably faster than one bytecode pattern. But if you have 100 patterns, the bytecode stands a pretty good chance of being faster.
And
yeah, now that you mentioned it, it makes a lot of sense. Thank you.
As far as compiling patterns ahead of time, you could like build the pattern tree ahead of time, but because the bytecode will have like attributes inside of it, some loading will have to be done at runtime.
Mm-hmm.
I posted in the chat for your reference the two past presentation. The first one was Jeff's internship results when he developed the first prototype, and the second one was River's presentation when it was what has actually been cleaned up and upstream in the final version. And today is really the language part of it. The previous one were the underlying engine and the optimization we were anticipating doing.
Yeah, and perhaps it's good to emphasize this is the it's very much work in process where we're eliciting feedback from the community with respect to the language and features and all of that. So this is not, this is under very active development. And, I think this is a very nice sneak peek of like how such a thing would work and, the better user experience, et cetera, that it could provide. But there's probably going to be a lot of discussions still to come on this course, on the RFC, et cetera. But if folks already have feedback, feel free to start discussions, that would be awesome.
Thanks.
Any last question? Anyone? Otherwise, we're at the end of time. So thank you everyone for joining today. Thank you, River, for presenting. This is very exciting. I'm looking forward for the RFC on this course. And well, see you next week, everyone. Bye.
Bye.
Bye.